Hey guys, I thought I would go do a chemistry problem with you. I'm just working out these problems right now, and I started another video, and I was like, dude, I'm doing terrible. So here goes. The question is, what is the pOH of an aqueous solution of 0.386 molarity of nitrous acid? So what I'm going to do is I Google search nitrous acid. Tells me it's HNO2, and so I write that down up here, and I need to know the Ka. So what I do is I go find it in a table or Google search it. Ionization constants. Nitrous acid is HNO2. It's 4.5 times 10 to the negative 4. And our Kw, our auto ionization constant for water, is 1.00 times 10 to the negative 14. So we're probably gonna need to know some of this stuff. So we just pulled it from the table. 4.5 times 10 to the negative 4. So we have our chemical formula here, and then what we need to do is we need to make our equilibrium equation. And so we know that HNO2 is going to dissociate in water into two different ions. It's going to dissociate into NO2 minus and H3O plus. The H3O plus ion. So what we're going to do next is we're going to set up our table. It's an ICE table, and it's going to help us to figure out how to create our equilibrium equation. So we put in our initial amounts. I is for initial. But we don't put anything for a liquid. H2O is liquid. This is 0. Everything initially on the right side is 0. C is for change. So change, it's going to be negative the coefficient in front of HNO2, which is 1. So negative 1x, which is negative x. We don't put anything in for water. And the coefficient in front of NO2 is NO2 minus is 1, so it's plus 1x or plus x plus 1x H3O. The next thing, the ICE, so E is for equilibrium. So at equilibrium, it's going to be 0.386 minus x. Nothing for water. And we're just going to have a static x for both of these because of the coefficient, basically. So our Ka is equal to products over reactants, which is going to look something like this. This is what I'm trying to do it, the conventions that I was taught. And this is going to be over, I wanted to do it like where there's a bar underneath, but over the reactant, and just include the aqueous solution HNO2. So then what we do is we back substitute our equilibrium, our x values, and our value for in our equilibrium into this equation. So Ka is equal to 4.5 times 10 is equal to over 386 minus x, and then we solve for x. It's going to be hard to solve for x here because the x in the denominator is going to make it a quadratic equation, and relatively hard. So what we're going to do is, if the way that I believe it works is if our Ka value times 100, Ka value times 100 is much less than the value of the initial amount, which is 0.386, then we can approximate, and so then 0.386 minus x becomes equivalent, a little squiggly, I don't know how to do that on the keyboard, but is equivalent to 0.386, because x is really such a small value that it doesn't matter. So 4.45 times 10 to the negative 4 times 100, move that decimal over twice, we get 4.5 times 10 to the negative 2 maybe, and that's still very, very small. So our new equation is 4.5. Our new equation is that, like that. So like that. No x there. So we solve this. X times x becomes x squared. So I'm just doing my calculator. 4.5 times 10 to the negative 4 times 0.386 is equal to 1.737 times 10 to the negative 4. And then we're going to square root, so second square root, second answer. So we're going to square root that value, and we're going to get x is equal to calculator. X is equal to 0.01317959296, which is equal to the number of hydronium ions that we have in the equilibrium concentration of the equation. But we want to know the pOH. So what we have to do is, I think I need to convert it to pH. So I need to convert this to pH. So what I believe, and I could be wrong, is pH is equal to negative log of our H3O concentration. And that is negative log of answer is equal to 1.88 equals pH. And then once we get that, remember that pH plus pOH is equal to 14. Therefore, pOH is equal to 14 minus 1.88 equals 14 minus 1.88 equals 12.12. We always use 2 decimals for pH and pOH. Yay! So this is what we did. And that's how you do that. So.